So when I draw my three-dimensional coordinate system, I typically draw it the way you're thinking. I like to draw my upward z-axis vertically, my y-axis to the right, and then my x-axis coming out at me is the way I kind of think about it. And you can kind of angle it as much as you want. So people will kind of go this way sometimes. That's totally fine. Sometimes I like a steeper kind of thing. So you could do that, or you could do something more like this, where you kind of go like more like that. Or you can even go wide, right? It kind of depends on what you're trying to draw. But the whole idea here is right that all these axes are at right angles to each other. So that is a right angle, that is a right angle, and that is a right angle. And so is this, right? There's a right angle. There's a right angle. And there is a right. But some people like to draw this differently than other people. So it is also totally acceptable to draw it as, some people do it kind of very symmetrical, where they're like, there's Z, and they kind of, I'm not super good at drawing it this way. Sorry, it's like this one looks terrible. We like to draw it like that, which is totally fine. When I draw it like this, I don't love it personally, but I kind of think about like the way I think about drawing this one is kind of trying to like take the center of an equilateral triangle and draw the lines to each of the vertices. That's kind of a weird way of thinking about it. Like when I know I did a bad job of it there. If you think about it, like this is kind of making an equilateral triangle like that. That's another way of doing it. I don't love doing it that way, specifically because it makes it harder to graph things in three dimensions. Like having the nice YZ axes be kind of what I think of as on the page makes it easier to graph things. So when I'm thinking about this, I'm thinking about YZ being like on this plane that is the piece of paper. And then even though X I have to draw on the paper because I'm drawing a three-dimensional thing in two dimensions, I'm still thinking about X kind of coming out at you or at me. So one thing I often do when I think about graphing in three dimensions is thinking about the room I'm in. So if I'm the student, if I'm one of you all, I like to think about that corner over there being the origin. And then that line up there, the periodic table is next to, is your z-axis. The line on the bottom of the ground running to the right is your y-axis. And the line to the left over there is your x-axis. And I should point out that those are all the positive sides of the x, right? Y to the right is positive, x to the front is positive, z up is positive. The floor below me, like if I went down to the room below me, z would be negative. And if I went to the room behind me, x would be negative. And if I went out the wall, outside over here, y would be negative. The room we're in, if that's the origin over there, we're in the first octant. We're in just like in two dimensions. Let's talk about it. We'll talk about a few things here. So in two dimensions, you have four quadrants. X is positive, Y is positive, quadrant one, and then we just label them this way. Specifically, quadrant one is where everything is positive. In quadrant one, X is positive, Y is positive. In three dimensions, we have a similar notion. So in three dimensions, well, again, if I draw the whole thing, so this is where things can start to get kind of, be careful. So I'm going to draw my z-axis. I'm going to draw my z and my y-axis just like I'm drawing a normal kind of two-dimensional thing. And then I have my x-axis poking out at me. So my x-axis is coming out this way. And then it's also going back that way. So there's my three-dimensional coordinate system. And this first octant where X is positive, Y is positive, and Z is positive. So essentially kind of everything in this eighth of three-dimensional space, right? Everything in here. I know that's not all of it, kind of get the idea, right? All of that out here in front and right and up, that's the first octant where everything is positive. We don't have names for the other ones. Like it's not like this is the second one and that's the third one, right? There's no other way of like describing the other ones. So, but we talk about the first one being where everything's positive. Questions so far? Definitely stop me if you have questions. So the 3D stuff can be a little bit weird, I think. Yeah. So yeah, the way he draws it here, yeah, I feel like especially the way he draws it, I'm looking at his notes. A couple, like the first couple ones he does, he's got Y like straight out to the right, but then like as you go further on, things get a little like not straight. Not that I should ever be one to criticize anyone else's drawings, because mine are obviously not amazing, but I personally would encourage you to default to the way we're doing it here, which is Y straight out to the right, Z up, X out towards you. Just as a point of interest, I should draw my video here. Sorry, Alexia. There, hit myself here. Also, let me give you the attendance. Oh yeah, please fill out the attendance form when you have a second. Here's the attendance form for you, Alexia. Sorry, the same thing. Oh, I should just point out that this is the standard way of doing it, but technically, someone could, and sometimes people do weird things like this, where they say this is X positive. So whenever I'm labeling an axis, I'm always labeling the positive side of the axis. Right? That's why we label X and Y here, not like X and Y there. So here's X, here's Y, and here's Z. So Y is kind of going back, and X is going out to the right, and Z is going up. The real thing here that has to always be true is we have to obey what's called the right-hand rule, where this is the way I was describing it as if you lay your fingers along the x-axis, and with your right hand, so the right hand rule, okay, use your right hand. Lay your fingers along the x-axis, curl your fingers towards the positive y-axis, and then your thumb should point in the direction of the positive z-axis. If I do it the other way, like for example, if my x-axis were this way and my positive y-axis were that way, then I'd lay my fingers on the x-axis. I'd turn my hand over so I could curl them towards the y-axis, and then my thumb would point downward. That would be the direction the z-axis would need to be to obey the right-hand rule. It's not too big a deal, but it is the way we typically draw our three-dimensional coordinate system for math. Sometimes there's this thing called the left-hand rule people do for physics stuff, but that's not this concept. We won't talk about that. All right, so graphing stuff in 3 dimensions. Let's talk about plotting points, I guess. Sure. So you know what? Sure. I guess I'll show you how I do it, and then maybe I'll show you some better pictures that I have over here that I did not draw. And maybe I will. Yeah. Okay. So let's say I want to plot the point something like, I don't know. Got examples over here. Let's say I want to plot the point 1, 3, 4, which is my x, y, z coordinate. So I'm going to draw my usual x, y, z coordinate system. And I'm just going to make up numbers. So right, so I know I'm going to be going 4 at the most in any direction. 4 that way, that way. And what I'll point out is that the lengths along the x direction shouldn't be as big. Because what you've done, so you might not be able, don't actually. So what I've done, right, is I've taken my ruler length. Let's say my length of 1 was this long on the x-axis. I've taken that and I've tilted it this way. Does it look as long? No, it's not. It doesn't look as long. It's supposed to be as long, but it's not going to look as long. So these should be like a little bit shorter. It doesn't have to be a ton shorter. They should be a little bit shorter. I'm not great at making that happen when I do it, but that's what I do. So then I'm going to go 1 in the x direction, 3 in the y direction, and 4 in the z direction. And you kind of go I kind of go all the ways, meaning I'm going to go 1 this way, 3 that way, and 4 this way. And then I kind of go all the ways, meaning, so I'm going to go over 3 and up 4, like that. So there's the point where x is 0 and y is 3 and z is 4. I'm going to go over in 1 in the x direction and up 4. So maybe like that. So there's 1 in the x direction, 0 in the y direction, 4 in the z direction. And I can also find this point here, which is 1 in the x direction, 3 in the y direction, and 0 in the z direction. And then from any of those points, I can kind of fill in the last part. So from here at the point 1, 0, 4, I'm going to go 3 to the right. Or from here, I'm going to go 4 up. Or from here, I'm going to go 1 in the x direction. And that point right there, that's your 1, 3, 4. I should mention, no one really ever asks you to plot a point in 3-dimensional. Like, it's not a thing we do. It's good to have an idea of how you find points in 3-dimensional space. So if you're trying to graph something that has more than just a point, you know where things go. But no one's ever asked you, like, where does this point? I mean, maybe it could come up on a quiz or something to like graph a point in 3-dimensional space. Okay. For the most part, not really a thing. Here's another maybe slightly nicer looking picture of the point 2, 4, 6. Same idea though. You're going 2 in the x, 4 in the y, 6 in the z. Or first 6 in the z, 4 in the y, 2 in the x. So you can kind of get there in lots of different ways as long as you do all things. But I'm really kind of, when I'm doing it, I'm not just doing this. I'm really kind of finding this point and this point and this point, and then kind of doing that to find where they kind of cross to get a good idea of where it is. Usually I'm always thinking of it as like the corner of the box with those dimensions that is the opposite corner of the origin. That's how I think about plotting a point. Okay. What else to say? Lots of things to say, actually. I would also talk about let's talk about the coordinate planes. So in 2 dimensions, you have the x-axis and the y-axis. And the way you typically find, so just kind of back up a little bit, 2 dimensions, the x-axis is really when y is equal to 0. Right? The horizontal line, y equal to 0, is your x-axis. And similarly, the y-axis, wow, that's a really excellent y I've just drawn there, is when x is equal to 0. It's also how you find your x-intercept and your y-intercept. Find your x-intercept by setting y equal to 0. Find your y-intercept by setting x equal to 0. Well, in 3 dimensions, you get similar kinds of things, except now, if you're going to set, say, like, let's start with z equal to 0. Well, that means you're going to get x and y being anything you want. You're going to get x, y plane, or is what I like to call the floor. So if I draw my system here, let's do this here. So I'm always trying to make enough room here. So z equals 0 is all the xy plane, because I can't go up or down, but x and y can be anything I want them to be if they're not in the equation z equals 0. So here, or here's part of, I should say, the xy plane. Obviously, I can't draw all of it because it is infinite. Just like I can't draw all the line because it's infinite. But there's part of the xy plane. Xy plane, where z, your height, is equal to 0. And then back here, in the yz plane, y and z can be anything. You can go as much up or down as you want, as much left or right as you want. But what does x have to be if you're living in the yz plane? So like if I'm right here, I'm right here, and I've gone over, I don't know, maybe 3 and up maybe 3 as well. Here's some point where the y coordinate is 3 and the z coordinate is 3. What's the x coordinate? Did I move forward or backwards at all? So what's the x coordinate? It's definitely 0. In the yz plane, x has to be 0. And then finally, the one that's always the hardest for me to draw. So here we haven't moved left or right, but we can move up or down as much as you want and forwards or backwards as much as you want. Here is our XZ plane. And in this plane, we have to have the Y is equal to 0. Because they're not getting any left or right movement. The reason we talk about this specifically is a lot of times we'll talk about the trace of a graph or of a function of 3 variables. And the trace is just what you get in each of the 3 coordinate planes. Which I think he mentioned in his notes here. Yeah. Yes, he did. Yeah. Okay. So we'll get, so it's kind of, so the way I kind of think about it is if you took whatever your surface was and cut it, like really sliced it with a plane, it'd be what you were left with just in that plane. So for example, if you took a sphere and sliced it with a plane, what are you left with? A circle. We'll see that a little bit later on here, but that's kind of vague. Like I'm really just talking about like more like physical objects here, but like, yeah, we're talking about just the 2-dimensional thing you get when you cut a 3-dimensional surface with some plane, either a horizontal plane or a vertical plane or another vertical plane. Yeah. So then we start talking about how to actually graph things. And there's lots of things to graph, and it's always kind of a mishmash because how much are we really going to do? Let's talk about some graphs. So we can graph something like y equal to 3. What I want to point out is when you're graphing an equation, if any variable isn't showing up, it means you can move freely in that direction. So here, if I'm graphing y equal to 3, it means the x values can be anything and the y and the z values can be anything. Meaning all I have to really be concerned with is making sure that all the y values are 3. X and z can be anything else. So what I can really say here is I can move up or down as much as I want. And I can move forwards. Now, when I move forward, I try to draw my forward movement parallel to the x-axis. So if I move forward, I can move. My rule is in my other pen bag. That's the pointing. I can move forwards or backwards as much as I want. So what I'm really getting here is this entire plane has been shifted 4 over from the origin. And again, my drawings are suspect. This plane, right? That's been moved 4 over from the origin, or to the right of the origin, I would say. This is the plane. Oh, sorry, not 4, 3. I apologize. I was sorry, not 4, 3. So this is y equal to 3. Every y coordinate in this plane is 3. The x and y coordinates are amazing. So like if I go, 1 forward and 1 up, that point there would be the point 1, 1, 3. Or if I moved 1 forward and 2 down. Oh, sorry. No, oh, I made a mistake. Not 1, 1, 3. 1, 3, 1. Right, the y coordinate's 3, and it's definitely x, y, z. That point would be, sorry. I can just, oh, look, it's part of the plane. That's the point 1, 3. I know you can't, I'm like trying to draw in here like you can see anything. That's the point 1, 3, 1. And down here, when I move down to, that's like the point 1, 3, -2. But anywhere in this plane, the y value is 3. X and z can be anything. So, again, I want to stress this because it comes up often-ish. If you're missing a variable, it can be kind of anything. Or what we say is that variable is free. Free to be anything wants to be. Just like when you graph the line y equals 5. Like if you're graphing in 2 dimensions, if I graph the line y equals 5, well, we know it's a horizontal line. What's x? Well, x can be anything because it's not in the equation. So x is a free variable. It can be free to be whatever value it wants to be. Same idea here. It's just now we have 2 dimensions of freedom. Both x and z are free here. Okay, let's look at a couple more examples. Let's say I want to graph z equal to 6. Well, same idea. It's just that now all the z values are going to be constant and x and y can be anything. So essentially, this graphing y equal to 3 is parallel to the xz plane, where y equals 0. Graphing z equals 6 is going to be parallel to the xy plane, where z equals 0. So all I'm doing is taking my floor, my xy plane. I always call the xy plane the floor, because it's just like the thing you think you're right. There's the xy plane right down there. Taking the floor and then moving it up 6 to be like the ceiling, if you want. So maybe like this is 6 high. I'm saying great. It's going as much that way as I want, as much that way as I want. Here's the plane z equals 6.
So that top one is 6.
Which point? This one right here?
Yeah.
Not just 6. It would be, what are the 3 coordinates going to be? Right, 0, 0, 6. Because I haven't moved forwards or left or right. I've just moved up 6. And then like this point out here, maybe I've moved 3 forward, and this is the point 3, 0, 6. Maybe this point I moved, I don't know, 8 to the right, and this is 0, 8, 6. Just making things up, really. Right? Obviously, we keep going. We just can't draw it that way because we only have so much time to draw a plane. All right. Sorry, if I heard someone say something. And then just to kind of see if we actually did both of these. So if someone said to graph y equal to 3 and z equal to 6, well, that means we're only left with 1 degree of freedom. X can be anything you want it to be. Y and z are stuck being 3 and 6 respectively. So it's essentially going to be where these 2 planes intersect each other. So here's what that's going to look like. So here. So yeah, let's try it. Let's draw the z one first. Here's my z equals 6 plane. And here's my 3. And here's my y equals 3 plane. And then this line where they cut each other, that line is where both y equals 3 and z equals 6. And x can be anything, which is why that line is moving backwards and forwards in the x direction. That's the only direction we have freedom in.
Wait, which one is?
Sure. So, which one? What? Well, not the point where they intersect, the line where they intersect. So if you take 2 pieces of paper, and if this one cut this one, so they were like that, right? They would meet exactly in a line where they touch each other. That's what we're getting right here, this blue line where the red plane and the green plane are intersecting each other. And there's no other really good way of describing it other than saying y equals 3 and z equals 6. It's kind of annoying, but it is what it is. All right, let's look at some other things. Still continuing with this idea of having degrees of freedom. So let's look at, we say we want to graph. Oops, maybe you want to see this. I guess I gotta zoom back out. Apologies. This is really loose. I should bring a Phillips next time in here and tighten that up a little bit. So let's graph the equation x squared plus y squared equal to 9. So if we were graphing that in 2 dimensions, what kind of shape would we get? Circle. Start at the origin, raises, 3. But in 3 dimensions, we're still gonna get the circle, but then what variable am I missing? Z, so that means I can move this as much up or as much down as I want. So I take my entire circle. It's in the XY plane. Here's my circle. Okay, let's see. 1, 2, 3. 1, 2, 3. Kind of like this, sure. Yeah. Nope, nope. Okay, so this is where my drawing skills start to be not great. There's my circle in the XY plane. So in the XY plane, I've got x squared plus y squared equal to 9, and also z equal to 0. But z equal to 0 wasn't a requirement of this graph. So what we're going to do is we're just going to extend this up and down. So we're going to get a cylinder. I should probably just do this, yeah. So drawing my, I still like to draw the circle first. Here's my. What I would really do is I would just do the horizontal part and then try and make a circle that you know looked flat. So here's my best shot. That's pretty good. There's my circle in the XY plane. And then I'm going to extend it upwards and downwards, but really it's easy to draw upwards. Now I should point out, it's not right. It's just like the around part of the cylinder. Right? It's not everything that's inside the cylinder. It's just this surface. It's kind of like oh, what's it called? The cardboard inside the paper towel roll, right? Like when you got, or inside the toilet roll, right? After you're done with the toilet paper, done with the paper towel, you're left with this cylinder that has some radius, but it's not filled up inside. It's not a solid, it's just a shell. So here's x squared plus y squared equal to 9. And I would say specifically, this is a circular cylinder. Now you might wonder why I'm emphasizing the circularness of it, because you might think all cylinders are circular. That's not true. In math, we use the word cylinder kind of grossly. A cylinder can be kind of really any curve that you let extend in one direction or another. So for example, yeah, I probably have enough room. Let's graph. You know, like when you cut your thumb, like at the very end, right by your nail, and it's just like, it's really like, it's not cut, but it's like, it was cut. It's just it's making it hard to write with this hand. So apologies. So let's graph the cylinder. And it is a cylinder, even though it's going to look weird. Z equal to x squared plus 1. So before I graph a thing in 3 dimensions, I often like to graph it in the 2 dimensions that might matter the most. So here, I'm going to think about what it's going to look like in the XZ plane. I'm not going to worry about the Y at all. So that's just a normal looking parabola shifted up 1. It's going to look something like this. So here's z equal to x squared plus 1, and also notably y equal to 0. I haven't moved it in the y direction at all. So now let's actually draw it in 3 dimensions. The problem, not problem, just the thing to be aware of here is that in 3 dimensions, my x is coming out towards me, not to the right, and my z is still going up. So there's my x, there's my y. So I have to take this XZ plane and kind of tilt it so that it's looking like it's coming out towards you, not like it's flat on the paper. So I'm going to draw it. Here's one, and it's look kind of like this. Right? I've taken that thing and I've tilted it a bit. So right, I've twisted it this way. Here was my oh yeah, I can do this, yeah. Right, so here was my parabola facing you, and then I said, oh, but it really needs to look more like that. So it kind of has a different, right? And it's hard to, it takes practice to visualize it. But what I'm kind of trying to point out here is essentially like these points are at the same height on the parabola. Zoom in a little bit so you can see that better. And then we're going to extend it in the y direction. So I'm going to shoot this over way to the right. Way to the right. Do the same sort of thing. So it actually looks a lot like what I just did. It kind of looks like a piece of paper folded up into a parabola, like that, going as far that way and as far behind me as I want to. It also keeps going up as well, right? It still keeps going that way, and that way, that way, that way. We just don't usually draw those arrows to indicate that because we don't. So here's our parabolic cylinder. We call this a cylinder, which might seem weird, but we do. So basically any kind of graph with missing one variable and is curvy looking, we call a cylinder. Like we wouldn't call the planes cylinders because they're planes, but anything like this where you just take some kind of curve and shoot it off in one direction, we call that a cylinder. So you can do it for like the square root. Or you could say, I want to graph, yeah, let's do that. Let's say I want to graph, I'm trying to think about which way to draw this. It looks the least terrible. Let's try graphing z equal to the square root of x, which you might want to see. So again, I know that I was going to do square root of y, sorry, z equal to the square root of y. So we know in our yz plane, this should look something like this. There's our usual square root going off to the right. So then in my three-dimensional x, y, z coordinate system, well, again, actually, I'm set up. That's why I really like doing this one because it's set up kind of already. I'm going to get the same graph. I should use a different color. And then it gets to move in the x direction as much as you want. So I would try my best, and this is where it's probably going to fall apart, to translate this same graph. Well, this is where like using a tablet would be excellent because you could literally, I think, copy this thing, move it down so it's starting here, and then yeah, I'm super jealous of you all right now. I'm going to try it so you can do that thing where you do that, and then kind of like connect them up. So that connects with that. That connects with that. That looks pretty okay. I think you kind of get the idea. It looks like, again, right, like it's taking a piece of paper, which is what a lot of these cylinders look like, and right, it looks like the square root graph, just moving as much as you want forward and backwards. Sorry, Alexia, if you can't see what I'm doing with the paper as well, but the idea is, right, we've got the square root thing, take this paper, make it the square root, and then kind of go as much forward or backwards as you like. Sure. So what I did here was I took my curve z equal to the square root of y along in the yz plane where x equals 0, and I shifted every single point this much in the x direction. At least I tried to draw it that way. But, and then again, it's not perfect. This is actually, one second, right? This is an excellent time to inform you, if you're not already aware, of a pretty useful three-dimensional graphing tool. Where are my things are there? It's called GeoGebra. Where'd you go, GeoGebra? Yeah. Sure, nice. I mean, like, it's not perfect, but it certainly graphs relatively easy things. So, like, for example, if I wanted to graph z equal to the square root of y, there you go. And you can, what's cool is you can click on it and you can like turn it around. So there's your x-axis in red, your y-axis in green, and your z-axis in blue. And oh yeah, it looks kind of like what I was saying, right? It just looks like a piece of paper that's done doing the square root thing. So this is definitely, I mean, not necessary, but can help you kind of just visualize it. And you can zoom in and zoom out. I'm just zooming out. It doesn't really look that much different, right? Because it just, yeah, it's kind of neat. It's also really neat for seeing how things intersect each other. So then if I wanted to graph like the plane y equal to 4, then it shows me where they intersect, and they intersect in a line, not too surprisingly, I think. They intersect in a line, y equal to 4 and z equal to 2. And x can be anything. So yeah, you had the question, Ryan?
Yeah, so, back at the z equals x squared plus 1. so
Oh,
y-
sorry, that's not what I meant to do. Sorry. Sorry, you were saying.
Whatever variable good, you can move it along this line.
Correct. Yes, you move it, you basically move your graph parallel to itself in that direction. So here, since I didn't have any x's, I moved the graph in the x direction. In the previous one, since I didn't have any y's, I moved the entire parabola to the right in the y direction. And just for completeness, let's try one that was missing a z. Oh, actually, we did one missing a z. The first one was missing a z, right? We had x squared plus what? Oops. We had x squared plus y squared equal to 9, and we took our circle and moved it in the z direction. That's kind of the idea, is that if you're missing a variable, you're going to move your graph in that direction. Like just kind of, you're going to kind of just keep translating that graph, that same graph in the 2 dimensions, piece by piece, further and further. Okay. How much time have I got? Okay. And then sometimes we graph things that are not just parallel to another coordinate axis plane. What I mean by this is you could graph the plane. So kind of like how a line, we always know the equation of a line. If you mentioned just like y equals mx plus b, it's a linear function. You've got y to the first, you've got x to the first. You don't have any other powers of any other variables. In a similar way, in 3 dimensions, if you have all first powers, you're going to get a plane always. Meaning, for example, if I wanted to graph, say, like 2x plus 3y plus z equal to 6, I know right off the bat that that's going to be a plane. Because every power of x and y is either 0 or 1. In our previous examples, right, like we had y equal to 0 or y equal to 5, z and x were both raised to the 0th power, they weren't there. But if you have everything, they have to be raised to the first power. To graph this one, well, how would you graph a line? You would find the x and the y intercepts. How would you graph a plane? You would find the x and the y and the z intercepts. So to find the x intercept, you set y and z equal to 0, and you get 2x equal to 6, so x equals 3. Find the y intercept, you set the other 2 variables equal to 0, and you get 3y equal to 6, so y equals 2. And finally, with the z-intercept, same deal. You set x and y equal to 0, you're going to get z equal to 6. So then I've got x equal to 3, y equal to 2, z equal to 6, which maybe I didn't space this out quite well enough. Oh well. And then you kind of just connect the dots like you would if you were graphing a line. So that little triangle there is part of the plane that is described by this equation. It obviously keeps going on, right? Like it continues on that way, and that way, and that way, and that way. But usually when you have a plane like this that has an x, y, and z intercept, we typically just draw the portion of it that's between those intercepts because it's easy to do. Let's talk about spheres. So just like a circle, in 2 dimensions, what is a circle? I mean, I know like that seems like a dumb question, maybe. But a circle, when you boil it down to it, the way a circle is defined is it's every point that is equally distant from the center of some certain distance. A sphere is the same thing. A sphere is every point in 3-dimensional space that is equally distant from the center of the sphere. Just like a circle in 2 dimensions, a sphere in 3 dimensions is all points equally distant from the center. So actually, if you really want to just like derive the equation for a sphere, it's not hard to do if you think about the distance formula. So let me show you, this is kind of cool. Let's say, here's a sphere with some center. Let's say the center, let's actually make it real numbers. Let's HJK stuff, whatever. Let's just use real numbers. Let's say the center is 1, 2, -3. Notice I didn't draw the XYZ coordinate system, just not to make it weird. And let's say the radius is, 5. So that means every point on the sphere, this point here, XYZ, this point over here, X1, Y1, Z1, this point over here, X2, Y2, Z2, any of the infinite number of points on the sphere is a distance of 5 from the center, which is 1, 2, -3.
Is that 1, 2, -3 at the baseline or just a
No, just a made up point. We could have picked anything. More generally, and we'll write the general formula in a second. People use like what do they use for? Gosh, for circles it's usually like H and K. For spheres, I don't know what the third letter they use. I have like H, K, and L maybe. I don't know, I'm gonna make something up. It'll be just fine. So how do you find the distance between 2 points? All the distance formula. There's 3 dimensions. You're just adding on the third coordinate. So the distance between 2 points is the square root of the difference in the x coordinate squared plus the difference in the y coordinate squared. And then if we're going 3 dimensions, plus the difference in the z coordinate squared. So if I want to find the distance between this point and this point, check it out. It's going to be x minus 1 squared plus y minus 2 squared plus z minus 3 squared. And we know, because of the way we've drawn it, that distance is how much? It's 5. And now I'm going to do one thing to make it look more like the equation of a sphere. I'm going to square both sides. To square both sides, I'm going to get x minus 1 squared plus y minus 2 squared plus, I would write this as z plus 3 squared equal to 25. And that is your standard equation of a sphere. Center is 1, 2, -3, radius is 5. More generally, here's the general equation. X minus h squared plus y minus k squared plus z minus l squared equal to r squared is the equation of a sphere with a center of HKL and a radius of R. Question: is the center of the sphere a point on the sphere? Not. It's still the most important point we care about, but the center of a sphere or the center of a circle is not actually part of the sphere or the circle. And we can see that if you plug in the point, or if you plug in the point 1, 2, -3 here, 1 minus 1 is 0, 2 minus 2 is 0, -3 plus 3 is 0. Does 0 equal 25? No, that center of your sphere doesn't satisfy the equation of the sphere. That's okay, it's not supposed to. But it's just worth noting that, oh yeah, the center of a circle or the center of a sphere isn't actually a member of the circle or the sphere. It's still the most important point, but it's not actually on the circle or on the thing. Okay, got a few minutes left. So then let's talk about the kinds of questions we like to ask. So we like to ask the kinds of questions like, what's the center and radius of the following sphere? We're gonna make it nice. No, we're gonna make it, yeah, we're gonna make this x squared plus y squared plus z squared plus 8x minus 6y plus 2z plus 17 equal to 0. So I will point out, I know this is a sphere because I see 1 times x squared plus 1 times y squared plus 1 times z squared and no other higher powers of x, y, and z. It's okay to have x, y, and z to the first, but we can't have anything else. More generally, we know it's a sphere if you have x squared plus y squared plus z squared, and they all have the same coefficient. It'd be perfectly fine if they all had 3 as a coefficient or 9 as a coefficient or whatever, but they have to have the same coefficient. But then to know or to find the center and the radius, we have to do some work. We have to be able to write it in the standard way, which is the way we just talked about. And the way we do that is by completing the sphere. So we're going to group all the x's together. And I'm going to leave myself some space afterwards. The y's together, y squared minus 6y plus something. And the z's together, z squared plus 2z plus something. And then I'm also going to bring the 17 over to the other side as negative 17. And whatever I add on the left, I also have to add on the right. Okay, so to complete the square here, I take the coefficient of x, which is 8. I divide it by 2, which is 4, and I square it. That's going to give me 4 squared, which is 16. Add it on the left, got to add it on the right. So the reason we do that is because when you add 16 here, it allows us to factor x squared plus 8x plus 16. And x squared plus 8x plus 16 factors how? Right, it's x plus 4 times x plus 4, which is x plus 4 squared. And that's why it's called completing the square, because when you add this number in here, it gives you some quantity squared. And the reason we're allowed to do this is because as long as you add 16 to both sides, you're not changing anything. But that's the number we have to find, is you have to take the coefficient of x to the first, divide it by 2, and square it to get you that back. Because what's happening here is 8 over 2, which is 4, is the number where 4 times 4 gives you that number, and 4 plus 4 gives you that number. And that's how you usually factor x squared plus something times x plus something, is you want numbers that multiply to that. Okay, great, 4 times 4, add to that, 8 times 8. Sorry, 4 plus 4, oh my God. Sorry. We're gonna do the same thing here. Negative 6 divided by 2 is negative 3, and negative 3 squared is positive 9. So here we're looking for numbers that multiply to positive 9 and add up to negative 6. That's negative 3 and negative 3. Those numbers multiply to 9, add up to negative 6. So this second part here, y squared minus 6y plus 9 is going to factor as y minus 3 squared. If I add 9 to one side, I got to add it to the other side. Finally, for z squared plus 2z, what am I going to add there? Well, yep, 2 divided by 2 is 1, 1 squared is still 1, so I add a 1. Add it there as well. And z squared plus 2z plus 1 is just z plus 1 squared. So this whole equation becomes x plus 4 squared plus y minus 3 squared plus z plus 1 squared equal to negative 17 plus 16 plus 9 plus 1 is 9. And now it's written in the standard form of a sphere, or the standard form of an equation of a sphere. And I've got my center is going to be, well, I'm always looking for the values that make everything 0. So what x coordinate do I need for my center? Negative 4. What y coordinate? And z coordinate is negative 1. And the radius is the square root of 9. Which, if it was like the square root of 7, we would just say it's the square root of 7. Since the square root of 9 simplifies, we're going to write it as 3. That's how you take a general equation of a sphere and write it in the standard way where it's actually useful. And it gives us information about what is the center and the radius. All right, we didn't get to, so I'll just say words here since we're out of time, but I'll say that when you're talking about finding the trace, which we'll talk about on Monday, the trace of a function, actually we can do it here. So real quickly, I could just say, what's the trace of this sphere What's the trace in the XY plane? So if you're living in the XY plane, what do we know is true in the XY plane? You're on the floor, how high are you? You're not high. You're zero high, right? You're not high, you're not low. Your Z is equal to 0. So if you're in the XY plane, Z is equal to 0. So we're literally just going to plug in Z equal to 0 into this equation. Look what happens. When I plug in Z equal to 0, I get X plus 4 squared plus Y minus 3 squared plus 1 equals 9. Or X plus 4 squared plus Y minus 3 squared equal to 8. So what's my trace? Well, in the XY plane, it's a circle. It's a circle whose center is -4, +3, 0, because I let Z equal 0, and whose radius is the square root of 8, which is 2 root 2, which is about 2.8. Let me show you on GeoGebra, just because I do think it is worth seeing this, and then you are free to go. I mean, I'm obviously. So, back. Hurry it up. Come on. Yeah, no, I don't care about you. Okay. So graphing my sphere, here's my sphere, X plus 4 squared plus Y minus 3 squared plus Z plus 1 squared, yeah, equal to 9. Oh, sometimes you're, darn it. Thank you, sorry, good call. It's hard to see what I'm doing over here sometimes. Over here, thank you, good call. There we go, there's our sphere. And what's nice about this is that it's already showing us the trace in the XZ plane or the YZ plane, because we can see where the flat YZ plane is cutting this sphere. And exactly cutting it in a circle. Now you could also write Z equals 0 if you want to make it more colorful, but it doesn't really change how it looks, right? So there is exactly in that plane there, the circle with a slightly smaller radius, right? It's not 3, it's square root of 8, which is a little bit smaller. Kind of neat. All right, that's all I got. Have a lovely weekend. Enjoy picnic day. Make good choices. Be safe. Have fun.